In my last video, we looked at how drugs like LSD bind to serotonin 2B receptors. In this video, we'll continue on that conversation and look at what happens after these drugs bind to receptors in a talk titled LSD Receptor Signaling and Dose-Response Curves. As usual in my videos, let's go through a bit of background information first. Last time we talked about this idea that LSD and psilocybin are psychedelic drugs that bind to G-protein coupled receptors, and in the last video, we looked at how LSD docks or binds to the serotonin 2B receptor. In this picture, we see the receptor, which is a G-protein coupled receptor, and it has these helical structures that cross the plasma membrane a total of 7 times, which makes it a G-protein coupled receptor. On the receptor, we have what's called an N-terminus, which is an amine that starts the amino acid sequence in the receptors. Conversely, we have a C-terminus, which is always a carboxylic acid, which ends the amino acid sequence in the receptors. Bound to the inactive state of the receptor, we have what's called a G-protein. This G-protein is always bound to the receptor when it is in its inactive state, or state of not any drug bound. The G-protein is comprised of 3 parts, an alpha, a beta, and a gamma subunit. We also see this thing called guanosine diphosphate bound to the alpha subunit of the receptor. In this slide, let's look at how a drug like LSD might bind to a G-protein coupled receptor and activate it. The picture on the left shows the ligand unbound to the receptor in its inactive state, which we just talked about. In the active state of the receptor, notice how the ligand is now bound. Let's try and look at the differences between the unbound state and the bound state in the G-protein. Let's first notice how in the G-protein has disassociated from the receptor. It has split into 2 subunits. The beta and gamma subunit remain attached together, and the alpha and GDP have remained attached together. But you should notice that instead of GDP in the active state, we now have a GTP. So we could indicate this as guanosine triphosphate, in which we have picked up a phosphate group in the active state of the receptor. These 2 pieces of the receptor are going to produce responses that we can measure in something called cellular signaling. Let's look at how we actually measure these signaling outputs exhibited by a G-protein coupled receptor when it is activated. These signaling outputs are known as dose-response curves, and they look like this. On the x-axis, we have concentration of drug, and on the y-axis, we have response exhibited by that concentration of drug from 0 to 100. If we bind a drug to a G-protein coupled receptor and we see that the response is 100% of the receptor's max, i.e. the receptor is fully turned on, we call these drugs full agonists. On the other hand, if we bind a drug to a G-protein coupled receptor and we measure the signaling output to be half the maximal response, we call these drugs partial agonists because they are not turning on the receptor fully. A partial agonist might also be defined as a drug that could turn on the receptor to 75% or 25%. It doesn't have to be 50%. It just has to turn on the receptor less than the full response. If we bind a drug to a receptor and nothing happens, it remains in its inactive conformer, and thus the G-protein will not break away from the receptor. We call these drugs neutral antagonists. There's this idea in pharmacology that receptors have constitutive activity, that the receptor will always be turned on a little bit even without drugs present. Drugs that turn off the basal level of a receptor are known as inverse agonists. These turn off the receptor completely. In the 1990s, a drug called rimonabant, a CB1 inverse agonist, was undergoing clinical trials. It was used as a diet or weight loss pill and was very successful with people losing weight, but the problem was it had severe side effects and was pulled off the market when a few people committed suicide after using the drug in a few clinical trials. On a dose-response curve, we can also measure the E-min, the minimum response exhibited by the concentration of drug. We also have what's called an E-max, which tells us how efficacious or effective the drug is. The other parameter we can get from a dose-response curve occurs what happens when we take that half maximal response of the receptor. For the full agonist, this would occur at 50%. If we then extrapolate this to the concentration of drug, we would see that it's occurring in this position right here. This concentration of drug is known as the EC, or effective concentration 50. This is the concentration of drug that is producing half the maximal effect of the drug. This is often important when we talk about things like potency in pharmacology, as a more potent drug will produce stronger effects at a lower concentration of drug given. You should also notice how if you were to do the same extrapolation for the partial agonist, you would notice that the drug has the same EC50 value. You could say that these drugs are equally as potent, but not equally as efficacious, because the E maxes are different. And now let's look at LSD's derivatives in a dose-response curve. In this curve, we're measuring LSD and its various derivatives' ability to recruit beta-arrestin at the serotonin 2B receptor. The first thing we should look at when we look at a dose-response curve is find the E-min and the E-max. We can notice that the E-min of each one of these four drugs is relatively the same. They're all starting off at a similar point at a concentration of -12 and -11. After that, things change with each drug. The Emax, however, is not occurring at the maximal system response, or the receptor max response, and thus none of these drugs are full agonists at serotonin 2B receptor. We can see that the Emaxs of each drug are relatively the same. LSD and SSAZ have about the same Emax. The next highest Emax is that of LSA, and then RRAZ has the lowest Emax. The next thing we should consider is the potency of each one of these drugs. We can do this by looking at the EC50 of each drug. I've placed a line approximately at this position to indicate the half maximal response of that receptor. We can see that slightly LSD is a little bit less potent than SSAZ because SSAZ's curve is slightly shifted up and left in relation to LSD. Thus, we would expect this drug to be more potent at the serotonin 2B receptor. The drug with the next lowest potency is that of RRAZ. RRAZ's curve is shifted to the right and down, and thus this is a less potent drug than LSD and SSAZ. The least potent drug on the curve is LSA. LSA is even less potent than RRAZ. There's an emerging idea in molecular pharmacology known as functional selectivity or ligand bias. The idea is this. When a drug binds to a G protein coupled receptor, that receptor will change its shape or conformation. Some of those shape conformational changes might cause beta-arrestin to be recruited better than something like GQ calcium flux or some other pathway. We call this idea functional selectivity or ligand bias. The idea is that we can promote one pathway over another. A good example of this is morphine. Morphine is an agonist at the mu-opioid receptor and causes beta-arrestin bias signaling, which causes a decrease in respiration and a decrease in GI function, which is bad. Molecular pharmacologists have taken advantage of this idea and made a drug called Truvena, which is a mu-opioid receptor agonist but causes G protein receptor bias, which increases analgesia, which is the effect of the drug we probably want, not decreased respiratory function and decreased GI function. Like any drug will display functional selectivity or ligand bias. LSD is no exception. The way we can measure functional selectivity or ligand bias is to measure the response of a receptor at two different pathways, but note it has to be the same receptor. Notice in this example how we have the beta-arrestin 2 recruitment at the serotonin 2B receptor and GQ calcium flux at the serotonin 2B receptor. The idea is that we are just measuring our drug's ability to recruit beta-arrestin at the serotonin 2B receptor. We can figure out what pathway it is ligand biased towards by doing the following. We compare the EC50 values, and whichever one has an EC50 value that is more negative, it will be biased towards that pathway because it is producing a stronger effect at a lower concentration. Let's start with the drug LSD and SSAZ. These have about an EC50 value in the arrestin assay at -9. If we look at where these EC50 values lie in the GQ calcium flux assay, we see them occurring at about -7.5. Because -9 is more negative than -7.5, we can say that LSD and SSAZ is arrestin bias. If we go over to RRAZ and look at where its EC50 value is at the arrestin assay, it's at about -8. If we compare the EC50 value to that of GQ calcium flux assay, we see that it's occurring at about -7. And once again, because -8 is more negative than -7, we can say that RRAZ is arrestin bias also. Lastly, let's look at the effect of LSA. LSA has an EC50 value of about -7.25 at the arrestin assay. At the GQ calcium flux assay, it is at about -6.75. Because -7.25 is greater or more negative than -6.75, we can say that LSA is also arrestin bias. So thus we have seen that all of the LSD and its derivatives display functional selectivity towards arrestin recruitment. In summary, there are three ideas I hope you learned from this video. G-protein coupled receptors consist of a receptor with 7 helices that cross the plasma membrane 7 times. In their inactive state, the G-protein is attached to the receptor, which consists of an alpha, beta, and gamma subunit. It's only when a ligand attaches to the G-protein coupled receptor that the G-protein can separate from the receptor, which causes it to have cellular signaling responses and produce drug-like effects. The second is know what information can be extrapolated from looking at dose-response curves. We looked at the Emin, the Emax, and the EC50. Lastly, if we have two different responses at the same receptor, know how to determine ligand bias. Ligand bias is important, as we saw with the case of LSD and its derivatives, because all of LSD and derivatives were beta-arrestin bias, which definitely has to do with the fact that it is a psychedelic drug. Till next time, hope you enjoyed.